So, as usual for TASI events, we sort of have one issue each week. Bring your this and bring your ID. And we will see you there for the bar. Meanwhile, Stefano's going to continue to talk about black holes and dark matter.
Cool. Yeah, really exciting barbecue night tonight. Yay. Cool. So, all right, let's get this started. And as usual, we're going to go back to reminding ourselves what we were talking about yesterday. So in the previous episode, we were talking about actual GR solutions to the vacuum Einstein's equations sourced by, in this case, a point mass of mass m. That's a Schwarzschild solution. And we emphasize that the Schwarzschild solution is not just the first GR solution that was calculated back in 1916 in the quietness of the trenches of World War I. It is relevant because of Birkhoff's theorem that tells us that that's actually the most general static spherical symmetric solution to Einstein's vacuum equations. We talked about the coordinate singularity that happens in the choice of coordinates that Schwarzschild's metric is written in. So that is not at all a worrisome singularity, unlike the physical singularity at r equals 0, which we call physical because we said you can construct an object that is coordinate independent, the Kretschmann scalar, and that object, undoubtedly, whatever your choice of coordinates is, diverges at r equals 0. So there is indeed a singularity that sort of, in a naive picture, is where all of the matter that has fallen into the black hole sits, in some sense. We then talked about the no-hair theorem and its subtleties related to where it does and it does not apply. So we talked about non-abelian gauge theories, and we talked about, sort of the background geometry where no-hair theorem holds and doesn't hold and so on. But the bottom line is that kind of like in Wigner's representation theorem, we can think of black holes as objects that are externally defined entirely by just a few parameters, namely a mass, an angular momentum that is improperly called spin. Again, we're talking about purely classical objects here. And so this is really the angular momentum, and a charge, which you can think about as the electric charge, but you can think also about as any, U of 1 dark type charge. Good. Speaking about charge, we briefly touched upon the metric that corresponds to a charged black hole. That also was calculated very early on because it does have spherical symmetry, so it's kind of easy to solve Einstein's equations in that case. The peculiarity is that the Reissner-Nordstrom black hole has two horizons, and what actually is relevant for the corresponding Hawking temperature, we're going to see more about that today, is actually the distance between the inner and the outer horizon. When that distance goes to 0, essentially the Hawking temperature vanishes and the black hole becomes extremal and it stops evaporating. And this might actually be pretty interesting phenomenologically, because you can imagine that as you proceed with Hawking evaporation, you get closer to the Planck scale. And then, all hell can get loose there because we don't really understand, what happens near the Planck scale from the standpoint of quantum gravity. However, what could happen is, and I see your hand, is you charge the black hole asymmetrically in, say, positive or negative charge, and then you can just reach extremality as you get close to the Planck scale, because a Reissner-Nordstrom black hole is extremal at the Planck scale if it contains, and we're going to see later today, just a few units of the electric charge. So it just takes an asymmetry in the charge of about 10 units at the Planck scale for the two horizons to collapse. The black hole becomes extremal, evaporation stops. It doesn't really ever become extremal. We were having a conversation yesterday with some of you, but it keeps shedding mass in the form of massless particles until you get very, very close to extremality. The black hole gets colder and colder, and essentially evaporation de facto stops. Something similar happens with Kerr black holes, which are spinning black holes. They also have two horizons. This is an axially symmetric, not spherically symmetric solution, so it actually took an extra 50 years. That kind of shows how much more complicated and painful it is to solve Einstein's field equation without spherical symmetry. Again, two horizons, and we're going to talk more about what happens in the case of curved black holes when it comes to Hawking evaporation. Then we sort of covered a weird topic, which is how the thermodynamics of black holes resembles the thermodynamics that you learn in kindergarten. And so, for instance, there is a zeroth law of black holes thermodynamics that says that the event horizon has a constant surface gravity. So it's kind of like, a body in thermal equilibrium having the same temperature throughout the body. The change of energy that essentially derives from the no-hair theorem. So there's a finite number of ways in which you can alter the energy of a black hole in just the same way as the first principle of thermodynamics tells you that there's a finite number of ways in which you can change the energy of a system. The entropy of a black hole always grows. And again, this is a classical statement, does not include Hawking evaporation. And number three, extreme black holes cannot exist. Then we took a big step and we looked at what happens when you consider quantum field theory, and so creation and annihilation operators in the context of general relativity. And I introduced very schematically the notion that if you have, I see your hand, oh, and that hand has disappeared. Did you have a question? Yes, please go ahead.
A little more of the no-hair theorem. There is a discussion in the literature about log number of black holes, for example, whether they're zero or not. And to my understanding,
What number of black holes?
log numbers, they talk about the structure of the black hole, whether it can be excited or not.
Okay.
And people are arguing that it's zero, therefore there's no structure, but I think it's a non-obvious statement
Yeah.
about the structure of black holes. So
Yeah. So,
look like at that discussion, the fact that you have the three numbers is not enough.
okay. So the question is, maybe there's some excited state of a black hole that is not captured by the no-hair theorem. So I'm not a formal theorist, but my understanding is that the no-hair theorem talks about static solutions. And so, you can have modes, for instance, after we actually see that experimentally, after a merger of two black holes, there is a ring down where the black hole kind of settles down to its asymptotic state. And in that ring down, you've got modes, vibrational, quasi-normal modes, I don't remember how they're called, but that is a transient. And so I believe the no-hair theorem really is a statement about the asymptotic state of a black hole after these transients. But thanks for the question. Yes?
So in the third law of thermodynamics and in other places too, we're continually talking about area rather than volume. Why is that?
Because we live in 4 dimensions. And so, when you talk about a surface in the space slice of a 4-dimensional space-time, you talk about 2 dimensions.
Could you explain that more?
Oh, yeah. So we live in 4 space-time dimensions. Let's take time away, so we have 3 dimensions. And so what is relevant is sort of the surface that encompasses this physical singularity. And so in 3 dimensions, the ds is a 2-dimensional object. Yeah. Cool. So the Unruh-Davis temperature is just a statement that, again, in quantum field theory, good morning, Sarah. In quantum field theory, when you have an accelerating observer, the accelerating observer sees the creation annihilation operators as producing particles in a thermal state with a well-defined temperature that depends on the acceleration of the observer. Okay, so it's just a statement about a change of reference frame from an inertial frame to an accelerating frame, and how the annihilation and creation operators look like from the standpoint of this accelerating frame. They look like a thermal bath. And so when you consider the geometry of a black hole, you consider what happens to an observer that sits on his horse at the event horizon. He sees a temperature. Actually, more correctly, he sees that at infinity, there exists a temperature caused by the gravity that accelerates him or her as an observer at the surface of the event horizon. And that temperature is called the Hawking temperature. And it's just the inverse of the mass of the black hole. We said, okay, that's cool. So let's calculate this temperature for a few interesting cases. We know that stellar mass black holes exist. And stellar mass black holes, as it turns out, are very, very cold. About 7 orders of magnitude colder than the thermal bath they're immersed in, which is the CMB. And so they actually don't evaporate at all. They accrete. And we're going to talk today about how that accretion works. Another thing that you can do once you know that black holes are sort of close to being black bodies is you can calculate from very simple-minded considerations that have to do with the Stefan-Boltzmann law, how they shed mass in the process of evaporating, right? And so that's quite simple, but it contains a few subtleties. It's quite simple to realize that this should be an exponent, m squared, that the rate at which black holes shed mass by Hawking evaporation goes like the inverse of the square of the mass. So here's the reasoning. The reasoning is just that the Stefan-Boltzmann law tells you that the power that you emit goes like the area of the hot object at temperature T times the temperature to the fourth. But we know that the temperature of a black hole, because of Hawking, is 1 over m fourth. And also we know that the area of a black hole is a Schwarzschild radius that is directly proportional to the mass. And so you have a mass squared here. And so this power is proportional to the mass loss of the black hole, which then goes like 1 over m squared. So that's a good mnemonic because, I like doing physics because you don't need to remember anything. Well, in this case, you do need to remember the Stefan-Boltzmann law, but it kind of makes sense. Okay, cool. So black holes are not exactly black, and we're going to see more about this today. And the reason why they're not black is that really what you're calculating in the Hawking radiation picture is you're calculating what happens to a free particle that lives in the background geometry of the Schwarzschild metric. And so what effectively you need to solve is the Dirac equation or the Klein-Gordon equation in the background metric of Schwarzschild. All right, so with a boundary condition that things die at the horizon. And so that ends up producing different results for the emission rates of particles with different spin. And that actually also depends on the spin of the black hole. So we're going to talk about this first today. So particles with spin are preferentially emitted by spinning black holes. And the naive picture that simple-minded folks like me have in mind is black holes with spin like to shed their spin, and so like to emit particles that carry spin. And what are these particles? Photons, for instance, but also gravitons. And so today I'm going to talk about the production of gravitational waves from Hawking radiation, which is something I'm actually working on right now. Yes?
Is the spin of a black hole a discrete quantity?
Oh, very good. It is not. It is not because it's a classical quantity. And classically spin, or rather angular momentum, is not quantized.
Okay.
Yeah. Okay, so spinning black holes are cool. They're cool in the sense that they're colder than the corresponding Schwarzschild black holes. So the temperature of spinning black hole with an effective spin parameter A star, which let me just remind you is the angular momentum of the black hole divided by its mass. So J divided by M, that's A star. So when you look at the temperature, you have a temperature which is parametrically lower, depending on the size of the spin, than the corresponding Schwarzschild black hole of the same mass. Okay, so if you look at this plot, this is very clear. So what this plot shows is the Hawking temperature as a function of the black hole mass for, I see your hand, Daddy, but just hang on a second. For a Schwarzschild black hole, that's a blue line. For a black hole that has a spin parameter that is 0.9, so it's spin pretty fast. Okay, so J over M is 0.9. And for a black hole that is essentially close to extremal, okay, 0.9999. All right, and you see that for a given mass, the quasi-extremal black hole is a lot colder, almost 2 orders of magnitude colder than the Schwarzschild black hole. So it also evaporates slower. Adi, take it away.
So normally I would, very, very classical particles, I would expect, with more energy mode, you would expect higher temperature. But you also have the statement that event horizon here is compressed.
Yeah.
So is it just that the person at infinity is less likely to receive that signal from this black hole because of that compressed event horizon?
Yeah, you sort of can think of it that way. Yeah, you can think of it that way. Good. So why does that matter? Why do we? Yes, question.
So why does it get colder when it spins?
So essentially, the reason is that what matters is not just the surface of the outer event horizon. It's actually sort of a combination of how distant the inner and the outer horizons are, and that in turn depends on the spin. So the closer the spin is to unity, the closer the two horizons are, and effectively the surface gravity decreases by a certain amount that is given by this expression. Does that make sense?
Very intuitive.
I don't have one. Addy offered one. Yeah. So it essentially has to do with how much acceleration an observer at the outer event horizons experiences, and that acceleration sort of goes down as the black hole spins more. Cool. So why is this relevant? Well, because, later today, we're going to talk about primordial black holes. And primordial black holes, sort of depending on how they form, can be either non-spinning at all or basically maximally spinning, or very close to extremal. And so as a mnemonic, when black holes form during radiation domination, sort of in the standard inflationary picture, they tend to not spin very much at all. So I'm not going to go through the details of what these various parameters in this plot from the Luke et al. Indicates, but look at the units. So these are the units of the typical, and these are distributions of primordial black hole spins, all right, that form during the radiation domination. The spin parameter is of order 10 to the negative 4 to 10 to the negative 3. Completely opposite is the case where black holes form in an early matter domination era. And in that case, folks, Harada et al. Here in 2017, have shown that A star tends to be very, very close to maximal. Okay, and again, I don't have an intuitive reason for why that is. Maybe the intuitive reason is that if black holes collapse because, in a matter-dominated universe, sort of matter infalls maybe in some, in some warpy stuff that carries angular momentum. I don't know, but this is what you have. So the extremal case is actually very relevant phenomenologically. We're going to talk about why primordial black holes might form in a matter-dominated era. Amelia.
Yeah, that's what I was going to ask. How do you get early matter domination?
Yeah, so very simple cases include the inflaton might at some point by itself, if it's very massive, dominate the energy density of the universe. An earlier generation of primordial black holes might themselves cause an early matter-dominated epoch. You can have gut-scale relics dominate. It's very easy because, as you know, radiation redshift is faster than matter. So if you have, at some point, the same amount of matter as radiation, you're slated to have a matter-dominated early regime. You know that, at CMB and at BBN, you have to be radiation-dominated. But before that, everything is game. Yeah.
So is this story also the case for black holes forming in the later matter?
Absolutely. So it is a little bit harder because, of course, it's only in a very, very late universe that you have matter domination. In fact, under about a temperature of 1 eV. So that's very, very late in the game, which means it's really hard to have large enough density perturbations. It's not impossible. We'll see why today. So good. So as I mentioned, Schwarzschild black holes, when it comes to calculating their sort of death rate, the rate at which they emit mass and they shrink, it only depends on the mass. And you have these gray body factors here that weigh the relevant Boltzmann distribution of how you emit thermally particles. That's not from my book, but it should be in my book. And Anna, I uploaded my slides earlier today, so you got them. Okay, cool. Excellent. In the case of Kerr black holes, you have a slightly more complicated picture where at the same time, you got to keep track of how you shed mass and how you shed spin. All right, so you have a tangled set of differential equations. And again, this is all in the slides which are uploaded on the wiki, so you don't need to write those formula down. What I want you to remember is that you have an equation for dA star dt, and again, A star is the spin parameter. Actually, it's a slightly different version of the spin parameter. Here's a square there. I actually don't know. Yeah, it is. It is like that. And so that's the evolution equation, which contains a slightly different object, which is this G of M A star, same gray body factor, but a slightly different structure. And again, you have to keep track of the shedding of spin and the shedding of mass in calculating the evolution of your black hole. So why is this relevant? Again, this is relevant because I truly hope that we will find a way to detect Hawking radiation. And if we do, things look completely different for a Schwarzschild black hole versus a close to extremal spinning black hole. Okay, so let me tell you what this is. This is a plot that shows you the emission rate for photons, spin 1 particles, for 3 black holes that have exactly the same mass, but have different spins. Okay, so same mass. I see your hand, just 1 second. But in one case, you have 0 spin, and you emit photons with this spectrum. Looks a lot like a black body spectrum. This is the 0.9 effective spin parameter, and this is the quasi-extremal case. Notice that, as we saw before, the Hawking temperatures of these guys are very different, right? Again, Kerr black holes are cool, and so they have lower Hawking temperatures that are, these vertical lines, blue, green, and red. But look at the spectrum of photons that get emitted. Not only do you emit more photons, you also emit harder photons, meaning more energetic photons. So this is phenomenologically very, very relevant. And you can imagine that when you set constraints from the fact that light black holes evaporate and you take into account spin, these constraints go all over the place. Yes, your question. Yeah. So yes, so the question is, how do these formulae change if you take into account the fact that a black hole might be immersed in a thermal bath? So these formulae change in the sense that, the equation, for instance, for the mass of the black hole will get terms that include the accretion. And we're going to talk about that today. When you accrete stuff, you also add typically angular momentum, right? Because if you have an accretion disk, obviously, you're shedding a lot of angular momentum inside the black hole. So the way in which these equations change is sort of only, you don't really affect these functions, because these functions, don't really care about what happens outside the black hole. However, the black hole itself does get additional terms to the equations describing the mass change rate and the angular momentum change rate in ways that, again, we're going to look into later today. Adi. Yep.
2em, is that like E over m, or is E something else?
Oh, yeah. So this is a typo. It's 2e over m. Yes, thank you, Adi. You have good eyes, huh? Despite the glasses. Yes.
What's the deal with these wiggles, especially in the red?
Yeah, so the wiggles, you probably remember that we saw wiggles in the gamma function. So the wiggles are just sort of a property of how the gray body factors behave as a function of x with the right form of x. So it's kind of like an effect that has to do, again, with solving the Klein-Gordon equation in the metric of a black hole. So you have certain, oscillations that depend on a combination of the energy of the particle that you're solving the Klein-Gordon equation for versus the mass of the black hole. So it's pretty non-trivial, but that's where it comes from.
Can you think of it as kind of some sort of back reaction?
Oh, I don't know. I don't think so, but maybe. So what's the picture you have in mind of back reaction?
I guess, there are highly energetic photons being emitted.
Yeah.
Maybe, some mass and energy and spin is being shed, and then maybe the black hole slows down a little bit in terms of the spin or something.
Oh, I see what you're saying. I don't think so, because these photons really don't care about with these photons. Okay. So you to calculate this and that, you just solve that equation, again, Klein-Gordon equation at this particular energy. But you don't really care about what happens at that outer energy. There was not. Yes.
If you look at the star are a little bit non-zero, you'd also get that jump, or is it there a smooth transition?
Yeah, so the question is, there seems to be a big jump here that is shared by both solutions of a rotating black hole. Does that jump only depends on the fact that you have a non-zero spin? I don't think so. So what I think would happen, and again, this plot is actually stolen by the author of Black Hawk, which is a surprisingly easy code to install. It's a pain in the ass to run, but what you can do is you can install Black Hawk and just solve it for, do this exercise for like a spin of 0.1 and see whether a spin of 0.1 goes all the way up here. My intuition is that it would sit kind of in the middle, but I don't know. I haven't done that exercise. Cool. All right. So what does the mass and spin parameter evolution of black holes look like? Again, same three black holes as before. This is Schwarzschild. This is Schwarzschild. So this is as a function, so it's the mass evolution as a function of time in units of the lifetime of the Schwarzschild black hole. Okay? So it's basically time to complete evaporation in units of the lifetime of the Schwarzschild black hole at that mass. And as you can see, if you turn on the spin, you actually shed mass faster. This is sort of the curve that shows you what happens to the spin as the black hole evaporates away. So at the end point, when the black hole dies, you have zero spin and you have zero mass, obviously. And you see here that there is a dashed line for the Schwarzschild black hole. Obviously, evaporation does not add any spin. And so that's kind of the qualitative picture of how the evolution of mass and spin in evaporating black holes looks like. That's not a question, or it's a question in process.
No, it needs to process.
Okay, no problem. I'll be sitting here. We're going to have barbecue tonight, so plenty of time. Okay, cool. Yes?
I just want to make sure I'm getting the right influence from this. I thought you said that the curved black holes evaporate slower because they're colder. But this seems to indicate that they're evaporating more quickly because they're shedding their spin.
Yeah, so that's a very good question. So it's actually a little subtler than that. So at any given mass, the statement is, at any given mass, if you have some spin, you have a lower temperature. But that is different from saying that one evaporates quicker than the other, right? So if you go back to the equations, you see that the change in mass is actually correlated with the change in angular momentum. And so, while at the same mass you have different temperatures, that doesn't mean that the evaporation rate is bigger for one than the other. Does that make sense? You make a very good point. So it is non-trivial. Yes?
That's the theory that the rotating black hole can have larger gray body factors.
Exactly.
And at a lower temperature, the gray body factor.
Exactly. Yeah, so the gray body factor really, and it kind of makes sense if you go back to this plot, right? So at the same mass, the gray body factor for the spinning black hole tells you that you shed a lot more photons than for Schwarzschild. So that's exactly, thank you very much. Yeah, so that's the right picture to have in mind. Yes?
So maybe I missed this, but what's the utility of the Hawking temperature for a spinning black hole?
The utility?
I mean, for a non-spinning black hole, I mean, it kind of gives you the black body spectrum nicely.
Mm-hmm.
But then we just had this whole discussion. It's colder, but it's actually radiating.
Right,
more.
right.
What's the use?
Yeah, so the use is we want to calculate curves like this. We want to understand how mass and spin evolves in the case of a rotating black hole, of a spinning black hole. And we want to understand what, phenomenologically we should be able to observe. So for instance, if you want to set a limit on how many rotating black holes there are, about how they emit particles, right?
Sure, but then, I mean, I'm looking at the Hawking temperature here.
Yeah.
And I mean, naively, I would think, okay, if the Hawking temperature is low, it's not radiating very much. But then we see right here
Yeah.
that that's kind of the event.
So that's back to her question. So it is. So one statement is what the temperature is, and another statement is what is the spectrum of the particles that you emit. The subtlety here again is the gray body factors are different if you have a spin in a black hole. Yes.
Time that is in the CMB, so the CMB also has a temperature, right?
Mm-hmm.
And then I was thinking for the Schwarzschild, whenever the Schwarzschild the temperature of the Schwarzschild black hole is larger than the CMB, then they start to evaporate, but before
Yeah.
that they freeze.
Yeah.
Is this picture still valid for the rotating black hole?
Yeah.
Okay.
Yeah. So yeah. So so I think the point you're getting at is, rotating black holes spit out a lot of photons compared to Schwarzschild black holes. So wouldn't they start evaporating sooner, even if their temperature was the same? So it's kind of immaterial in the sense that really you want to calculate this emission rate and see whether the accretion rate that you get from the stuff outside the black hole is larger or smaller than this emission rate. So that really tells you whether or not you are accreting or evaporating. So it's really a combination of the m dot that you get from Hawking and the m dot that you get from accretion, all right? So that really tells you what the black hole does, and we'll get there. So you might, looking at this plot, you might say, well, then, any black hole today should have a very low spin because, you shed spin pretty efficiently. In Kip Thorne, and I don't know where this number comes from. What this number is the Relic spin of a black hole. So 1 minus the spin of the black hole today. So how extremal can black holes be? And again, depending on the initial spin, you can have large spins in black holes today as well. Okay, so this kind of depends on the mass, but black holes today might still be spinning, and so it is relevant to think about the phenomenology of spinning black holes. So what I was going to mention is that an interesting byproduct of black hole evaporations, especially those that carry spin, is gravitons. All right, so gravitons are perfectly kosher spin 2 particles that you can calculate the gray body factors for. And in fact, this was done back in 2011 by Dolgov and Agili. And the calculation is fairly simple. So the calculation is also very interesting because emitting gravitons means that you're producing gravitational waves. Okay, that's exactly the same statement. Semi-classic, I see your hand, just 1 second. And so you can calculate the density of gravitational waves that you spit out as a function of the gravitational wave frequency at emission. And that's essentially, a simple function that again depends. This is sort of simplified. You don't have the gray body factors here, so that's part of the reasons why we are redoing this calculation. I'm going to tell you the next reason as well. What is important, thinking back to what Juna was talking about yesterday, is where the spectrum of gravitational wave that you emit from Hawking radiation of gravitons peaks. All right, and the bad news is that it looks this way. The peak of the gravitational wave spectrum from graviton emission of black holes, and I believe this is a 1 gram black hole, and this is a 10 to the 5 grams black hole. I should have put this on the slide. But look at the frequency. It's insanely large. It's an insanely large frequency, and that's too bad. And I see people back there being very disappointed by this frequency being too large. Right? If you have a 1 gram, so a very hot black hole that evaporates, it emits gravitons to the frequency of like terahertz. Now, as you've heard from Juna, we are good at detecting gravity waves on Earth at about a frequency of 1 hertz. Okay? When we put the same technology in space, we are probably going to be very good at a millihertz. And then we are actually quite good at very, very low nanohertz frequencies with PTA and all that swing and dance. But people are, and this is actually, it's not my joke, this is a conference that took place at CERN just a few months ago. people really want to push the limits of high-frequency gravitational waves. And again, you see here BBO and stuff, and this is LIGO. Actually, it's more like 10 to the 3, I guess, the peak, whatever. We're far away from these frequencies, right? And there were a couple of questions, so let's go first here. Yes?
This happened earlier, and then we redshifted. Did we get something interesting?
Yeah, so this actually assumes as early as possible. So basically, you create these things at t equals 0. And so, you've already digested all of the redshifting that you had. Yes? Oh, yeah.
Why is n effective 100 in this estimate?
Yeah, so these black holes are very, very hot, right? 10 to the 5 grams is a black hole that is way above the TeV. And so they take an effective to be 100 is that all the degrees of freedom of the standard model are relevant. And so, roughly speaking, unless you have a lot of dark degrees of freedom, is about 100. Let's see, there was another question here, and then you. Yep.
Could you think about treating these gravitons that are being emitted as particles and look for the particles rather than look for the gravitational waves? Because these very high frequencies mean energy, right?
Yeah. So, the guy pushing this is thinking hard about that. Yeah. So, yeah, absolutely. Yep.
Presumably, these will also decay to all the new BSM fields if they exist that we haven't discovered yet. So could that make up the dark matter? Could that be a production for the dark matter?
Yes. I'll talk about that tomorrow quite a bit. Yep. A very good point, Amelia. Yes.
What about near extremal black holes? Because those will have a smaller temperature and smaller frequencies, and maybe we'll get something in the band.
Yes. So definitely your best bet here is to do this game with spinning black holes. But I'll tell you more. What we think is an even better bet is to lower the Planck scale. So if you lower the Planck scale, you can have a much lower mass. And remember that the mass of the black hole is what drives where the peak frequency is. So the trick that we are trying to play is maybe the best case scenario is one where you have extra dimensions. And so effectively, you lower the Planck scale sort of arbitrarily. Some people say even close to the TeV. And so if you have a TeV instead of 10 to the 5 grams, this peak frequency goes down by many, many orders of magnitude. And maybe you're back in a game of detecting these gravitational waves. Let's see, there was another question there. Yes?
I was going to ask about the sensitivity curves, and they generally have this shape that goes like this. I understand that for each experiment, there's some optimal frequency.
Yeah.
Is there some other explanation?
There is. So the most interesting explanation is why these curves go up very quickly. And you know what that is? Is the frequency of earthquakes. So if you have a gravitational wave detector on Earth, the biggest pain in the ass are experimentalists walking around, and that produces sort of mini earthquakes that are upsetting your detectors. And the rest is seismic noise, which really peaks at a few hertz. Noise is very hard to beat on Earth, and so that's why you see this loss of sensitivity. Here you're in space, so you might say, what is this? And honestly, I don't know. I don't know why the sensitivity decreases, but it probably has to do with the fact that lower frequencies mean bigger distances, and you only have a finite arm length in your detectors. And so when your inverse frequency gets the same size as the arm length, you're kind of struggling because you only see part of the gravitational wave, right? Because the wavelength of the gravitational wave is much, much bigger than your detector size. So I think that's what drives the loss of sensitivity, even in space.
And at high frequencies, these suffers.
At high frequency here, at high frequency, you have to contend with, I think, for these detectors is like shot noise of photons that gets in the way, if I remember correctly. My alma mater, Pisa, has one of these gravitational wave detectors just outside in the countryside. And so many of my friends, when I was back there, were working on this and scratching their heads primarily on seismic noise and shot noise from photons. Because ultimately, you're shooting photons, and I think that's the shot noise that kills you at very high frequency. But I'm not an experimentalist, so I don't really know. But I think that's it. And then you might ask, what is this? And I think that is the size of the universe. At some point, a gravitational wave has a wavelength at low enough frequency that is the size of the universe. And at that point, even PTA is like, forget about it. Yes?
Could you remind me what the masses are?
The masses of what?
In the plot of the frequency.
Oh, yes. 1 gram for the red. Sorry, I should have put it on the slide. And 10 to the 5 grams for the red.
Okay.
Yeah. So here's a really cool paper, this Dolgov and company. I mean, Dolgov is kind of a weird guy, but this paper is very good. Okay, cool. So very good. One more fun use of, yes?
In some of the previous slides, we saw that black holes with a mass of 10 to 15 grams should have already evaporated.
Uh-huh.
So when I'm looking at this 10 to 5 curve black hole, am I assuming that it's already evaporated and so we are getting sunlight from black hole?
Yeah, from very high redshift. So she was saying, well, maybe redshifting, so these things are assumed to be completely evaporated at very, very early times. But, you emit gravity waves, so they just travel, they just redshift. And so that's what happens. Maybe another caveat is you can try to enhance the redshift by modifying cosmology at early times. I don't know. That could be another clever thing to do, but I don't know. Maybe you can think about it. Okay, so can we use black hole thermodynamics to constrain dark sectors? So that has been in the back of my mind for a long time. And I think the answer is yes. And there's one really trivial thing to do, which sounds very stupid, but that you can certainly do. And it turns out it's actually not as stupid as it sounds, which is to take the lightest black holes that we know exist. So say LIGO black holes or some astrophysical black hole that we're pretty convinced, maybe not a media, but I'm pretty convinced exist, and assume some formation time, so some age associated with these black holes. And then you can constrain the number of light degrees of freedom, because if there's too many light degrees of freedom, the black hole would have evaporated away, would have not survived. And so it's actually an estimate that you can do in one line. So the estimate goes like this. So the black holes that we know exist are about, stellar mass. And so they have a lifetime of 10 to the 67 years. And we want them to stick around for about the age of the universe, which is 10 to the 10 years. And if you add n degrees of freedom, your lifetime, roughly speaking, if this number of degrees of freedom is much larger than the 100 degrees of freedom of the standard model, your lifetime of the black hole is reduced by a factor 1 over n. Okay? And so how many light degrees of freedom can we possibly have? Well, roughly speaking, 10 to the 67 divided by the age of the universe, 10 to the 10. So roughly 10 to the 57. Okay? Yes, that's a very funny number to think about. Okay? But don't underestimate string theorists, because there might always be a string theorist saying, oh yeah, my theory predicts the existence of 10 to the 110 vacua. And so 10 to the 57 maybe is not such a stupid number. No, but you can seriously think about, what Carrasco was talking about yesterday, amplitudes. You can think about what happens to amplitudes relevant for the LHC if you have a large number of degrees of freedom. As it turns out, the LHC also provides constraints on this insanely large number of degrees of freedom. And they're worse than this. They're actually worse than this. So as far as I know, if you want to constrain in sort of the simplest possible way, but also the best possible way that I'm aware of, the number of light degrees of freedom in a dark sector, this is the best argument you got. Yeah?
So if you have some number of light degrees of freedom hidden in the dark sector in the early universe, those are going to be radiative species, right? So couldn't you also...
Maybe, maybe not. Maybe they live in their own little, dark universe, and it's fine. Maybe they're not interacting at all, so they're not in thermal bath. Maybe they are not even produced in the early universe. They exist, but it's so hard to produce them that they're just not around. So there's many ways in which these things could exist in the early universe. Yes. Oh, okay, cool. Yeah, it is a good question, but you can always hide degrees of freedom in the early universe one way or another. Okay, Very good. One more thing that I've been sort of obsessing with is, okay, let's suppose that magically we can create a black hole today, and that the black hole evaporates away. If that's the case, then we can actually do particle spectroscopy directly by looking at the light curve of the black hole. And here's why. Because let's think about what happens if this is a plot that I didn't make, so I don't know why they call plus quark this thing, but I think they allude to the fact that if you have, say, supersymmetry, you're essentially doubling the number of degrees of freedom in a very natural and necessary way. And so black holes, instead of dying in this way, they die much quickly as soon as their temperature is on the same order as the mass of the SUSY particles, right? You cross over, and all of a sudden a black hole can spit out SUSY partners, and it evaporates away very, very quickly, right? And interestingly, and this, if you see the legend is wrong, it should be vice versa, and this causes a detectable change in the light curve, right? So what happens here is, this is again time to evaporation. So you're cruising in a very similar way as if you didn't have these new degrees of freedom, but then at this particular time, your black hole crosses over where the temperature of the black hole corresponds to the SUSY breaking scale, or to the mass of the SUSY partners. And so all of a sudden, you spit out a lot more photons. And in the case of supersymmetry, this game is a little bit non-trivial because, of course, SUSY partners that you produce in evaporation themselves produce photons. And so you enhance this curve because the SUSY partners decay and produce a bunch of photons. But also the light curve changes and you evaporate at least 10, 15 seconds sooner rather than in the standard case. And so what I am trying to figure out is, can we understand by looking at the light curve of evaporating black holes, how many degrees of freedom there might be in a dark sector, and where the dark sector mass scale is. So if the dark sector doesn't produce any photons, you won't have this jump, but you will have a tilt in the light curve. And you will have also a change in the spectrum of the photons. So I think that's pretty exciting. Yes, Amelia?
Sorry, how are you differentiating this from light from the accretion disk of the black hole?
Say it again?
How are you differentiating this from the light from the accretion disk of the black hole?
Oh, good, good. So the question is, black holes also spit out light because there is an accretion disk that contains particles that are energetic enough to spit out light. So these guys are very, very tiny. So it's almost impossible that they have an accretion disk. And the reason is that, to form an accretion disk, you need to, tell particles around you that you exist. But these black holes are so small that essentially you don't tell anyone that, you exist. And so you never form an accretion disk for these tiny black holes. There was another question somewhere? Yes, Adi, and then you. Yep.
What is your SUSY scale here? Is it natural?
Yeah, it's probably like a TV or so.
Okay.
Yeah. Yes?
Is this something that we could hope to observe?
Oh, I very much hope so. So the question is, how? All right, so, and here's my answer. So what these things would look like is very, very similar to a short GRB. All right, so, but there are very, very striking differences between what called an exploding black hole and a short GRB. And they're listed here, so I'm not gonna go through this. But basically what a GRB looks like is you've got the explosion, and then you've got sort of a phase where the GRB cools down and you have a tail. In the case of explosion of black holes, it's completely different because you have this runaway process and then nothing, right? After this, you get nothing. So is there hope? Well, people have written papers about GRBs that look a lot like exploding black holes. And of course, exploding black holes, we calculate, so you can see from here, they emit about 10 to the 30 seconds. So they really can be very far away. In fact, I don't know, but we can calculate how far away they can be. So you want to see at least a photon for your detector size. Let's say that you have a very large detector of like 10 to the 4 centimeters squared. So how far can this thing be to observe 1 photon every second? So you have 10 to the 30 photons per second, and you are at a certain distance d, and so the flux is this d squared, and you have to multiply this by the effective area of your detector, which, I don't know, let's say that we're looking for optical photons, or maybe, super high energy gamma rays, so we can use Cherenkov detectors. Water Cherenkov detectors are really large. There's this huge swimming pool in Mexico that is instrumented with little photomultipliers called Hawk. And Hawk is like a kilometer size detector. So let's see, a kilometer is how many centimeters? 10 to the 5 squared. Let's say 10 to the 10 to be really generous. Okay, let's say that this is 10 to the 10 centimeters squared. So what we have is that d squared can at most be, if I want 1 photon per second, has to be smaller than roughly 10 to the 40 centimeters squared, if I'm doing this right. So we're talking about 10 to the 20 centimeters away. And I told you that 1 kiloparsec is 3 times 10 to the 21 centimeters, right? And so what that is, 10 to the 20 centimeters, is roughly 0.3 kiloparsecs away. So how big is the galaxy? It's about 20 kiloparsecs. So we are about 8.5 kiloparsec away from the galactic center. We're talking about having this thing, within 300 parsecs of where we are, in the hope that we see 1 photon per second with Hawk. All right. So, if this is a galaxy, and you can clearly see that I'm an artist, all right, we are somewhere right here. We hope that this exploding black hole happens to be within a very small circle around us. All right. So that's the hope. Is it completely hopeless? Maybe, but I don't know. It depends on how, on how these objects are created in a very late universe. In a very late universe, because they have to evaporate quickly, right? They can be old black holes that all of a sudden are at the right point in their life to show us photons, because otherwise there would be many of them, and they would completely overwhelm us with photons from wherever in the universe. So the question is, how do you produce these things? And I don't know, I'm not smart enough, but I have a postdoc who is smart enough. His name is Will DeRocco. And so we have a couple of ideas, but primarily what you want is to have a bunch of subcritical thingies that might merge and might create for you these evaporating black holes. So you don't want these things to be the dark matter, but you want to have enough things around in the galaxy that they might merge and, maybe once every year produce within 0.3 kiloparsecs of where we are, these exploding black holes. Now, maybe that's crazy, but what I like to think is to prove Lenny Susskind wrong. So that's kind of my life goal in this time. And so Lenny writes, I'm a good friend of Lenny, so I'm just kidding, that the quantum theory of black hole evaporation will probably never even lead to direct observations or experiments. Maybe he's wrong. All right, we'll see. But either way, so here we are. So that's what we're going to do next in these lectures. I want to talk about how these things form. So we've seen how these super light black holes might form in a very late universe. But generally, if you want primordial black holes to be the dark matter, you want to produce them in the early universe. We'll see how. Then I'll talk a little bit about accretion. And finally, probably tomorrow, I'll talk about how can we tell whether dark matter is made of these primordial black holes. Yes?
Question about your last slide. So you're saying possibly very late time phase transitions could produce these black holes. Would those be phase transitions in the dark sector?
Maybe or maybe not. So I'll talk about that as well. So the idea is that if you have a phase transition, you might squeeze particles in the unbroken phase and create these clumps at very late times, sort of naturally. So that's another thing that we're thinking about. Yes?
Other signals from those late phase transitions that you might expect to see before you see these black holes?
Fantastic. So yes, so these phase transitions, if you want to squeeze particles and create these high density clumps, they have to be first order. And so as Juno was saying yesterday, any first phase transition produces gravity waves. So probably the best bet is through gravitational waves, but also ineffective, because ineffective is sensitive, for instance, to the injection of latent heat, and so first phase transitions do that as well. So a couple of ways, but what I don't know, and I'm really curious about, is suppose we are right now undergoing a phase transition. Is there any way to tell that? And I don't know. I don't think so. But we might very well be right now undergoing a possibly even strong first order phase transition without knowing it. So if anyone has ideas on how to tell whether the universe is currently undergoing a phase transition, please let me know, because I'm really curious. So for instance, there is a field that gets a VEV, and you have a large potential barrier between the broken and the unbroken phase. And so patches of the universe have the field, in the broken phase, and other patches, no. Yeah. So some new field that, kind of like the Higgs, but, with a critical temperature that is 10 to the negative 4 eV. I don't know. Okay, cool. So, the last thing that I want to talk about is what else can you do with primordial black holes that evaporate away? And I think Amelia was alluding to, maybe you can produce dark matter. You can do a lot more than that. You can do baryogenesis, you can do dark matter, you can do many, many things with evaporating black holes, so sort of S portals. So let me talk a little bit about how black holes, primordial black holes, can form in the early universe. So the general picture is very simple, and I'm sorry, this is a standard story first. So let's talk about how we think black holes arise from stars. So this is literally a one-line calculation, and the idea is, getting back to one of your questions earlier in the lecture series, at some point gravity wins over Pauli blocking, all right, over quantum pressure that comes from Pauli's exclusion principle. And there's actually a very, very straightforward way to calculate this. So suppose that you have n fermions, and you squeeze them in a radius r. So the number density of your fermions is n divided by r cubed, forgetting the pi's, forgetting the 4/3. All right, so the typical separation between fermions is on the order of the inverse cubic root of the density, and so that's r divided by n to the 1/3. And so in natural units, the Fermi momentum is, Planck's constant divided by that separation, right? Delta x, delta p, order 1, which means that the typical momentum, the Fermi momentum, is the inverse of the separation. Okay, so we have this Fermi momentum, and also if you have a bunch of fermions within a sphere of radius r, you have an average gravitational energy per fermion that is just, Newtonian gravity, that is just 1 over r times the number of fermions that are within r. Okay, so what we want to do to see whether or not Fermi degeneracy pressure can sustain this system of gravitating particles is we want to see whether the gravitational potential energy wins over the Fermi energy. And so literally, we are doing this very complicated exercise of asking when Gn m squared over r, wins over the Fermi energy, and we imagine that upon collapsing, the Fermi energy gets bigger and bigger, so the Fermi momentum gets bigger and bigger, so the Fermi energy is basically equal to the Fermi momentum, right? These fermions are relativistic. And so we want this to be bigger than n to the 1/3 divided by r. So there's one pretty interesting thing which happens, which is this. And then everything is pretty simple because you've got n to the 2/3, which you want to be equal to 1 over gm squared. And so the number of fermions that you have to have gravitational collapse is gm squared to the negative 3/2. Okay? So super simple. You have an exact determination of the number of fermions that are self-gravitating such that you collapse into a black hole. So let's see what that number is. And that number is a lot easier to calculate if you go from G to the Planck scale, right? So we know that the Planck mass is some function of G. And so if you rewrite this number in units of the Planck scale, it takes this very nice form of Planck scale divided by m cubed. So 1 second. So the Planck scale is about 10 to the 19 in GeV. And m presumably is a GeV for astrophysical objects. So you have 10 to the 19 cubed. What is that? It's 10 to the 57. 10 to the 57 is actually an interesting number because the sun weighs 10 to the 33 grams. And as we said in lecture number 1 gram is about an Avogadro number of GeV, therefore of nucleons. So the sun contains 10 to the 57 nucleons. And so our one-line calculation tells us that anything that weighs more than the sun, presumably at some point when you turn off the pressure that you get from nuclear reactions, should collapse into a black hole. Everything that is lighter than that will just hang around in the form of a white dwarf or a neutron star, right? And this is surprisingly a good estimate because, the actual correct estimate with all the bells and whistles is within a factor 2 of this one-liner calculation. And this is called the Tolman-Oppenheimer-Volkoff limit, which takes into account the fact that even if you switch off nuclear reactions, you still have nuclear interactions between fermions. And so that adds to the Fermi degeneracy pressure, right? Because you don't turn off QCD all of a sudden. And when you take that into account, you get about 2 solar masses. In fact, the estimate is sort of theoretically uncertain because we don't really understand QCD at super high densities, and we don't really understand what happens at these pressures and temperatures. But the current estimate, as far as I know, for the TOV limit is between 2.2 and 2.9 stellar sum masses. Noted that this is for a non-rotating neutron star. When you add rotation, you can imagine that you had a little bit of rotational pressure, and so the limit is higher by about 20%. So should we take this seriously? Well, it just depends on, yes, I see your hand. It just depends on what we see out there. And what we see out there are black holes that weigh 2.74. We know that very precisely because in this particular event, there was a neutron star event. As far as we can tell, I have a paper that says otherwise, but never mind. You produced a remnant that weighs 2.74 solar masses. So that's a black hole that formed, that exists. And so that is the sort of observational lower limit of how light black holes can be, compatible with TOV. And on the other hand, there is evidence for neutron stars that are as heavy as 2.5. So the cusp of when you form a black hole observation is here, which is, of course, very compatible with the theory estimate. And you had a question.
Yeah, thanks. So do black hole observations give us a constraint on stable, massive BSM bosons? Because you could pack more mass in potentially?
Yeah. So this is a whole big chapter. So you can use black holes to constrain light bosons in a variety of ways. Probably the most clever way is called superradiance. And this is a whole new lecture topic, which I can tell you about. But yes, you can use black holes to constrain light degrees of freedom in clever ways. Yes?
I'm confused what's going on here with the kind of microscopic picture. So
Okay.
we know we can't pack the quantum states of the fermions states they're going into at all from like a microscopic perspective when this is occurring?
Yeah, so that's a great question. And I can tell you, so actually just today, a paper that I wrote with some of my collaborators got accepted. And this paper had to do with the following. So suppose that you create a small black hole in the middle of a neutron star. How do we think about accretion of neutrons on this small black hole that might exist in the center of a neutron star? So within that question, we pointed out, for instance, that people had used a completely wrong picture of accretion. That was the Bondi picture. The black hole size that is sort of critical is such that the wavelength of neutrons is comparable to the size of the black hole. So you have to do the calculation in a quantum sense. And actually, Mr. Unruh kindly provided the right cross-section for us. But I'm telling you this not only to advertise my paper, but also because we struggle to understand how to treat neutrons in the core of a neutron star. We struggle because people don't really know. So there's ideas about superfluidity and collective modes of neutrons. There's ideas about other states of matter that are at present unknown. So the short answer is that those densities, we don't really know what happens to QCD. So super high densities, very high temperatures. We don't know the phase diagram of QCD well enough to tell exactly how to think about neutrons in that way. So the same is true here, right? Before a neutron star collapses into a black hole, how do we think about neutrons? Well, presumably not in this super simple way. Presumably they're not just a Fermi gas. And so part of that story goes into this evaluation of the nuclear effects that neutrons in these extreme temperature and pressure conditions feel. So again, we don't know. It's a very interesting question, and it is a question that is being sort of tackled observationally more and more, because in neutron star events like GW170817, you can actually use the gravity wave event to constrain the equational state of QCD in neutron star core conditions. So that's one part of the story. You can use the emission that you see off of neutron stars to do the same. So as you get better and better with observations, you might gain more information. But it is a very tough problem. It's a very interesting problem as well. Cool. So here we go. This is what will keep us busy for a little while, which is, other than from the collapse of stars or neutron stars, how can we form black holes? And this is the general idea of forming non-astrophysical black holes from fluctuations in density perturbations that are large enough that you essentially exceed a gene's mass and you collapse into a black hole. So the picture is very simple. The picture is one where you have a threshold for a density perturbation to be large enough that no matter what the density perturbation is made of, you are larger than a critical value, and in size, your density perturbation is of the same order as the size of the horizon, right? Because if the horizon is smaller, the universe there keeps expanding and you don't collapse. But when the horizon crosses the physical size of the density perturbation, and the density perturbation is north of a certain critical value, you necessarily form a black hole. Okay? So this is an idea that dates back to Zeldovich and Novikov in 1967, and then Hawking reiterated it just a few years afterwards. And the real question is, how can we have density perturbations where delta rho over rho is of order 1, right? Because you need a delta rho over rho of order 1. So that's a pretty good question, and that's what's going to keep us busy for the next, maybe half lecture. So primordial black holes are interesting for a number of reasons that I don't have any time to go into any detail, really. So for instance, evaporating black holes have been invoked to explain a bunch of emission processes that don't have a clear, simple astrophysical counterpart. This includes gamma ray emissions, such as the galactic center axis that Ben has been talking about, antimatter in cosmic rays, and I've lost many years of my career thinking about the positron axis, that cosmic ray experiments have seen. So these things might originate from the evaporation of black holes. People have talked about reionizing the IgM with PBH. And as we just did, they talked about GRBs originating possibly from black holes explosions. However, even if black holes don't evaporate, if they exist, they might play important roles in astrophysical processes. For instance, there are some anomalies in quasar lensing that need point masses of a certain size, and PBH have been invoked to explain that. The heating of stars in the galactic disk might work better if you have large, non-evaporating primordial black holes. There are some unidentified microlensing events that people associate with things called machos, and these machos might actually be primordial black holes. There's been a lot of talking about supermassive black holes being too large to form in sort of a standard model of black hole merger and accretion. So maybe the seeds for these supermassive black holes are primordial. And you can even think about generating galaxies from density perturbation seeded in the early universe by primordial black holes, and so on. Finally, folks at Johns Hopkins a few years back have made a big noise about the LIGO black holes, those mergers that LIGO observes being actually the merger of primordial black holes. So let me tell you in the last couple of minutes or so what the general idea is for forming black holes, not from stars, but rather from the collapse of density perturbation. So the idea is that if you have a cosmological fluid with a given equation of state, then it so works out that the Jeans mass that leads to a density perturbation of the size of the horizon to collapse into a black hole is of the same order as the speed of sound squared, and roughly that works out to be comparable to the equation of state W, which in the case of radiation, so if this density perturbation exists in a radiation domination phase of the universe, that's about a third. So you want a density perturbation really of order 1. You might say that is stupidly large, because we know from CMB observations the density perturbations in the early universe that seed the CMB power spectrum are very, very, very tiny. In fact, much tinier than 10 to the negative 5. I think the current constraints are at 10 to the negative 8, right? So how in the world can we hope to have these large density perturbations? Well, we have to look at scales that are different from the scales that pertain to CMB observations. And those are very, very large scales. But let's first think about what the mass of the black holes that are formed from the collapse of density perturbations are. And this is, again, a one-liner calculation. So we said the collapse happens when the horizon becomes of the same size as the size of the density perturbation. So what that means is that the mass of the black hole that you generate is the same as the mass contained inside one Hubble patch, okay, when the density perturbation collapses. So what is that mass? Well, that mass will equate, the horizon time, CT, when that is of the same size as the Schwarzschild radius of the black hole that you form, right? So I don't even have to worry about what the density is. I know that the black hole that forms will have this Schwarzschild radius, and this Schwarzschild radius must be equal to the Hubble horizon, which is the speed of light times the age of the universe. So CT equals mg over c squared, and I see multiple hands, just one second. So the mass of a black hole that forms when the universe was t old in time is c cubed t over g. It's a super simple estimate, all right? So again, the estimate is Hubble size, c times t, equals Schwarzschild radius, all right, which is mg over c squared. So in units that are sort of manageable, the mass of PBH that are born out of the collapse of density perturbations at the time t is 10 to the 15 grams divided, times t in units of 10 to the negative 23 seconds. Okay? So if you know when your density perturbations become the same size of the horizon, that's the time t, you have a way to calculate what the mass of the PBH that you form is. Does that make sense? Cool. Question?
Thanks. So is kind of the picture we should have in mind that in the very early universe, there's rapid expansion happening, and there are these large density perturbations. And
There might be. We don't know, but there might be.
and when the density perturbation is the size of everything in causal contact, that's when the collapse happens?
Yeah. So essentially, when the size of the density perturbation is of the same size as the horizon, then what physically happens, instead of the expansion going on, the universe is like, wait a second, I am no longer expanding because there is all this mass. So now I'm sort of reverting the expansion into a contraction, and that leads to the formation of PBH at horizon crossing of the density perturbation size. Yes, that's exactly right.
And does that require that we make some assumption about the universe outside of the observable universe?
No, it does not. Yeah, it does not. So we are out of time. Sarah.
I think the Hubble patch in this instance is not a causal patch.
Mm-hmm.
So there's a distinction. People call this a horizon. This confused me so much until last week. They finally got through my head. This is not a causal horizon. So if you think about it, imagine that this is happening in the context of inflation, for instance, causing these density perturbations. There's actually you can think about the entire inflaton condensate being already correlated, right? So it's not the case that when you cross into one of these Hubble patches, you're crossing through a causal horizon. There's a distinction. It's actually, the scale is set 1 over the Hubble constant.
Yeah.
That's not the same as saying that it's out of causal contact.
Yeah, so literally the statement is 1 over h equals the size of the density perturbation. Yeah, so it's the Hubble horizon that matters.
And is that larger than the region in causal contact? It's smaller.
Mm-hmm.
Okay.
There are many Hubble patches in the causal universe.
Yeah.
Got it. Because of inflation.
Yeah. So we're out of time. So I'm just going to stop here, and we're going to take it from here tomorrow. Cheers.